Okay, so in this problem we're given a much more complex circuit with 3 different power sources kind of looping back on itself, and there are 5 resistors all with the same resistance, 1.5 mega ohms. So this makes our life a little easier. We don't have to worry about all the different resistances, so it's going to be a little simpler in that regard, but nonetheless it's still going to be a complex circuit with 4 different loops and 3 loops and 4 equations. Alright, so the first step to do, first thing to do, define currents. Okay, so I'm going to take my colored pencil here and I'm going to define I1 as going in this direction. Why? It's completely arbitrary, but we just have to define the current and be consistent. If we're incorrect about this, you know, it'll come out later that one of them will be negative, and that will be okay. So I'm going to define I2 this direction. Again, completely arbitrary. And I will define I3 as this direction. Could have done it differently. This is the way I did it on the solutions I posted online. So I'm just being consistent here. Okay, so we have 3 unknowns. We need 3 equations to solve for them, but we will actually be able to obtain 4. So I'm going to give you all 4 equations, just so you know, so that you know you have options. So the first equation, I'll just label this equation 1. That's the simplest one, following the junction rule, which means that you see I1 and I2 are flowing in together at point B, and then I3 flowing out. So I3 is flowing out like that. So that means I1 plus I2 must equal I3. It has to be, by conservation of charge. You can't end up with more charge flowing out of a junction than you have flowing into it. So I hope that one is your easy go-to equation that makes perfect sense. And here we have 3 unknowns. Guess I can write it out. Okay. So for equation 2, now we're going to have to go use the loop rule. Okay, I stopped the video for a second because I wanted to relabel these in terms of what I did on the notes. So A, B, C, D, and A, B, E, F. So for the first loop, I'm going to choose A, B, C, D, A. B, C, D, A. All that means is I'm going from A to B to C, D, A to D, and back to A again. I'm making this one loop here. So I guess we should start at point A. So as we go from A to B, we don't encounter any kind of component at all, and we're going in the direction of I1. Now when we get to point B, the current changes because that's a junction. So we're no longer using I1 anymore. As we go back down this way, we're looking at current I2. But I2, we had chosen to flow in this upward direction. It was an arbitrary choice, but that's what we chose. We're sticking with it. So now we're going in the opposite direction of the current. As we flow across this resistor R, we are going from negative to the negative potential end to the positive potential end. And that is defined by the current flowing through it. If the current's flowing this way, potential is lost across this resistor. So that means if we're going the opposite direction, it doesn't mean that the resistor is adding potential to the circuit or anything like a battery would. It just means that as we go across from this point to that point, our potential in the circuit has increased. So that is going to be a positive RI2. Now as we go across this battery, we're going to subtract because we are going, not because we're going in the opposite direction of the current, but because we're going from the plus side to the minus side of the battery. So it's minus E2. So we're going the opposite direction across the battery. That means we're going to a lower point of potential. Now at point C, now we're reaching another junction again. So as we continue along to D, the current changes and we're back to using I1 again, because I1 continues all the way around from C to B. So as we're going now in the direction of I1, we must lose voltage across this resistor. It's minus IR1. Okay, so we're at point D. We turn, we go up through this battery. Now we're going from the negative side to the positive side of the battery. So voltage is increasing, so we're adding E1. So after the battery, we'll continue on through this resistor, again in the direction of the current I1. So that's minus RI1, all those sum to 0. I could simplify this if I wanted to. Let's see, I have two I1s, so let's just say E1 minus E2 plus RI2 minus 2RI1 equals 0. And I will call that equation 2. And again, two unknowns, I2 and I1. We don't know what those are. So now we use the loop rule again. Loop rule, and we're looking at, let's look at, say, BEFCB. So we're going around this loop now. In fact, to accentuate where I'm going, I'm only looking at this loop. BECFB. Okay, so starting at B, I move nothing here. As I start at E, I move down. I'm now moving with I3. I'm going through this resistor in the direction of I3, so that's negative RI3. I go in this, I encounter this battery. I go in the opposite direction of the polarity, so I'm going from positive to negative, so that's subtracting E3. I continue on through this resistor, so I have minus RI3 again. Now when I get to C, I'm at a junction. The current has changed because the current is splitting up. And I will now continue on with I2. I go across the battery E2 from negative to positive, so I'm adding that voltage. And then I go across this resistor going from positive to the negative side, so I'm subtracting RI2. So if I can group like terms for a moment, I have E2 minus E3. Sometimes I like to put these in parentheses because they're known values, so I just separate them a little more. Minus RI2 plus, minus 2RI3 equals 0, and I can call that equation 3. Now that's I can stop right there. I've got 3 equations and 3 unknowns. But just for completeness, I want to go through it and do the next loop, the final loop, which will be the exterior loop in the circuit, A, B, E, F, C, D, A. So that's the big loop. So I want to look at it this way, say, I'm just ignoring the part in the center and going around the outside. So I start at A, go all the way across nothing. I've got, the current has changed from I1 going from A to B to I3 going from B to E, but it's fine, there's nothing there. Now I go in the direction of current I3 across that resistor, so that's minus RI3. I go in the opposite direction across that battery, so I'm going from positive to negative, so I'm subtracting voltage, so I'm subtracting E3. I'm still going in the direction of I3 across this resistor, so that's minus RI3 again. To C. Now at C, the current is switching because it's splitting off, and now I'm continuing on with I1. And going up through the battery where I add the voltage E1 again, and I subtract RI1 at that resistor. So let's see, I can group like terms. Minus 2RI1 minus 2RI3 equals 0, and I'll call that equation 4. So I have 1, 2, 3, 4 equations and 3 unknowns. I can definitely solve that. So what kind of patterns can I notice? Can I eliminate anything right off the bat? Well, I can combine these two equations, right? And then I can just, I think the best way to really go about this is usually to insert equation 1 into one of these others. In this case, it's already solved for I3, so why don't I put it into equation 3? So I'll do it down here. Insert 1 into 3. So I have I3 defined already. I can insert this into equation 3. So this is epsilon 2 minus, not epsilon, excuse me, E2 minus E3 minus RI2 minus 2I3, which is now I1 plus I2 equals 0. Now I have to regroup the terms a little bit because I have an I2 here and I have an I2 there. So E2 minus E3 minus R minus 2R, so that's minus 3R I2 minus 2R I1 equals 0. So do I notice anything like that? Minus 2R I1 minus 2R I1, so I can combine this equation 3 that I have to rearrange down here and put that, add that to equation 2. But the first thing I'm going to do is multiply this by -1. Now I could just subtract the 2 and you get the same thing, but I don't know. For some reason when I deal with equations I'd rather multiply by -1 and add it. So let's do this over here. So this is, when I multiply this by -1, that's the same as switching these two. So I can just say E2 minus E1 minus RI2 plus 2RI1 equals 0. This is equation 2. And equation 3, the altered form of equation 3 with equation 1 put into it is epsilon 2 minus, or not epsilon, E2 minus E3 minus 3RI2 minus 2RI1 equals 0. Now I can add. When I add these two terms together, 2RI1 minus 2RI1, they subtract out. So I am left with E2 minus E1 plus E2 minus E3 minus 4, so I've got minus R minus 3R, so it's minus 4R I2 equals 0. Or I can say that I2 is equal to 2 E2 minus E1 minus E3 all over 4R. And this then is equal to 2E2, which is 2 times 90 millivolts minus 75 millivolts minus 20 millivolts for 4 times 1.5 mega ohms. So 2 times 90 times 10 to the negative third, because it's millivolts, minus 75 times 10 to the negative third, minus 20 times 10 to the negative third, all over 4 times 1.5 times 10 to the sixth ohms. And the result is, okay, 14.2 nanoamps. Move the decimal place over and now I have 10 to the negative 9, so that's 14.2 nanoamps. So what about I1 and I3? Well, I can go back to one of these equations. Okay, so one of these has R3 in it and I2 in it. Okay, so equation 3, that's the one we're going to look at, because it has I2, which we just found, and I3, which we're looking for. So E2 minus E3 minus RI2, and I'll move R3 to the other, I3 to the other side, that whole term. So that's 2RI3. I just took this term and moved it to the other side. So then I3 is equal to E2 minus E3 minus RI2 over 2R. So that then is equal to 90 millivolts minus 20 millivolts minus R 1.5 mega ohms times I2, which we've just found as 14.2 nanoamps, all over 2 times 1.5 mega ohms. So let's put that in our calculator. If I turn this lamp off, that'll help a little bit. Okay, so 90 times 10 to the negative third minus 20 times 10 to the negative third minus 1.5 times 10 to the sixth times 14.2 times 10 to the negative ninth over 2 times 1.5 times 10 to the sixth. So I3 then is equal to 16.2 nano